computer scientist, and I set myself a goal for this presentation, and it is to hopefully make you walk away with a little more knowledge of how AI works on the inside. You know, we talk a lot about AI applications and uses and use cases, but you know, as a computer scientist, I've been working in neural networks, which is an important branch of artificial intelligence, since 1991 as a student, and since 1993 for a living. And so I have an inward-looking view. So I look at what happens inside AI systems, and I'd like to talk a little bit about that to you, and hopefully send you home with perhaps a new idea of how to look at AI, how to think about AI when you read things in the news. So that's my goal. Now, you know, the next slide is a bit silly. We all know ChatGPT, and we all know these generative AI systems. This is one of my favorite images. I found it somewhere online by Michael Howe-Ely. It's very impressive, you know, this generative AI nowadays. I can't say otherwise. But to many people, the whole concept of generative AI is new. And trust me, it's not that new. It's been going on for many years. Here are two output works of generative AI. One is by a system called Aaron, made by Harold Cohen. And it was basically an artificial painting system, an AI painting system that he developed between 1987 and 2004. Or 2007, I think even. This particular work that I show here on the left is from 2004. You can forget that immediately. Another one by Simon Colton, who made a system called a painting fool. You feed it a newspaper article, and it creates a collage based on the content of that newspaper article. Anyway, these are examples also of generative AI. The weird thing is, at that time, we wouldn't call it generative AI. We would call it procedural content generation, but it's the same thing. It may work slightly different, but the concept is similar. Now, if you compare that to the output of nowadays generative AI systems, we see a difference. Look at the difference in quality between these old things, and I mean visual quality basically, and let's say the modern output. And there's two striking observations to be made. First of all, the mouse is running off. The level of complexity of modern AI systems, generative AI systems, is much higher than the old ones. And the realism, the diverseness of what they can create. Imagine that these systems like Aaron and the painting fool that I just showed you would be able to create many different paintings, but you know, they would be very recognizable as coming from the same system. That's not the case in systems like Midjourney or DALL-E 2, these image generation systems. But another big difference that we sometimes overlook is what I like to call the declarative nature of prompting. Up to, let's say, the current hype in AI, if you wanted to create something, you had to know how it worked. And as computer scientists, we call that working procedurally. You had to understand the procedures to create something, and then use the computer to actually go through these procedures. Nowadays, with modern generative AI, we work in a way that, as computer scientists, we call declarative working. Actually, I borrow these words from the programming context. So as computer scientists, we can talk about procedural programming or declarative programming, but it's similar to what happens now. If we want a computer system, a generative system, to output something now, we just tell it what we want. We don't have to worry how it works. You know, we don't need to understand the procedures. We just declare what we want. So it's a declarative nature of working. That's also a huge difference when you compare the modern systems to those, let's say, 10 years ago. Now, these two observations have a consequence. And that consequence is that due to this, you know, extreme realism in the output, but or this, let's say, this almost human likeness in the output, and this declarative nature of prompting, the way in which we interact with these systems, humans have a tendency, an increased tendency, to project human qualities onto these systems. When I say human qualities, we kind of like, you know, we like to think of these systems, that they understand what I want, or, you know, or that they have an intention. That's also possible. Or even that they possess this mythical quality that we refer to as creativity, that we don't even understand ourselves very well. These are consequences of these high levels of realism and complexity in these models, and also the fact that we work declaratively with them. Now, so talking about AI, I want to go a little bit, look towards the inside. So what is AI? What is it? What do I mean when I talk about AI? Now, sometimes it's difficult to explain, but I'm going to explain to you a little bit what it is and how it works. And usually that would take, let's say, a bachelor program, 3 years or something. I have 20 minutes, if I'm not mistaken, so I had to skip a lot, right? A lot. I had to skip roughly 3 years of classes, but I'm going to do my best anyway. Now, I'm a computer scientist. I'm also a nerd. You know, I was mentioned by a big Dutch national magazine as one of the 100 most interesting nerds in the Netherlands, and I read that as one of the biggest nerds in the Netherlands. That means I like to simplify things. I like to abstract things. I like to categorize things, and we'll see a little bit of that later on. So see if you can recognize the nerd in my presentation. But here's the first point where you should be able to recognize it. I like to see things in a very simple way. You know, so this is my simplified view of what machines and humans, you know, find easy. Now, what machines find easy, traditionally, is symbolic reasoning. What humans find easy is something that I'd like to call pattern recognition. Now, what are these things? Well, for example, symbolic reasoning is doing calculations, or ordering numbers, algorithms, things that we as humans are not actually that good at. Or, you know, you need a strong working memory for that. You need speed for that, things we don't have, right? On the other hand, pattern recognition is easy for us. You know, it's easy for us to recognize a dog in a picture, for example, or to understand speech, or maybe it's not easy to predict the weather, but, you know, at least that's also a form of pattern recognition. Now, conversely, these things are very difficult for the other party. So calculating symbolic reasoning is very difficult for humans, very easy for machines, whereas pattern recognition, and this is the point, is very difficult for machines traditionally. Recognizing a dog in an image is very, very, very difficult for a machine. That may sound weird, but it really is. Now, we humans, not only are we, let's say, let me look correctly at this thing, are we really bad at symbolic reasoning, we're also very lazy. So why do we have machines in the first place? We have machines to help us, right? To offload our tasks. You know, we don't want to do too much, so we have weaving machines, we have cars, we have bicycles, we have all these machines that help us. Now, given this little simplified view of what machines can do, you can understand why we invented, let's say, the basic calculator, the thing that helps us compute. You know, multiplications, divisions, those kind of things, right? It's a machine. It's good at, machines are traditionally good at symbolic reasoning, so why not make a calculator that helps us? We've done that many years ago. But we also like machines to help us in pattern recognition tasks. Tasks of pattern recognitions that require somehow to recognize patterns or to do inductive reasoning, basically, is another word for it. Now, as you can see, that's difficult for machines, right? So it took us way longer to make machines that can help us in that category of tasks than it took us to come up with a calculator, right? And it is exactly in this category of tasks that we find machine learning AI. So machine learning AI, and what that exactly is, I'll talk to you in a moment about. But it's basically what we now call modern AI, right? So the purpose of it is to help us, as any machine, but to help us with pattern recognition tasks, tasks that require us to find patterns in data, in observations, in perception, whatever, right? So this is a simplified view of why we have AI, to help us there in that part of the world. Now, if you go home, if you didn't know this distinction, and you know it now, you go home, you've learned something today, something useful, right? So you know, that would make me happy. Now, I mentioned here machine learning AI. So the word AI has been mentioned a few times already by Professor Piet and by Amanda. But machine learning is a word I just stuck to it. So let's look at this machine learning thing. Now, the way these systems work, these modern AI systems, these pattern recognizers, is very much like we humans work. Like if you guys go outside and you see a bird, you'll recognize it as a bird, right, or a dog. But let's stick with the example of a bird, right? It's not because your parents programmed into you the algorithm of what a bird looks like, you know, because if we would have to write down that algorithm, that sequence of steps, we would not be able to do that. If I would give you all a piece of paper and a pencil and write down and ask you to write down, how do you recognize a bird, right? Some of you may write down, does it have feathers? Does it have a beak? Does it fly like Superman? Well, that doesn't help us at all, because that's just transferring the problem. Then you still need to recognize feathers. You still need to recognize a beak. You still need to recognize flying from visual input, right? Which is just a transferal of the problem. So that's not the way to go. You cannot program this stepwise how to recognize a bird. So that's also not how we recognize birds. We recognize birds because we've been exposed to them many times. And when we were a child, we saw a bird, and perhaps you said, cat. And your parents would say, no, 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 that's a bird, right? Something like this. That's how it went. That's how we learned to recognize this pattern of what a bird looks like, right? And somehow that is now instilled in our brains, that pattern. Right? That's how we just recognize stuff. That's nothing very complex that I'm saying here. Now that is also how globally machine learning systems obviously work. And I'll go a little bit more into detail about how that works on the inside, right? So machine learning is formerly a sub-branch of artificial intelligence, but it's the one that's been growing over the years more and more and more. I'm from the machine learning branch since a long time. So what you need to know, and this is very important, is that they were not programmed explicitly to do a task. We didn't program them explicitly, this is how you recognize a bird, as I just said, right? No, they learn it from trial and example. And as doing so, just like us, they induce a model of the data from the patterns that it's in the data. Now this is an important concept. So it finds patterns in the data, and from that constructs a model to use. Now what can it do with a model? Just like we humans. If you go to the zoo tomorrow and you see this weird-ass bird that you've never seen here in Leiden fly around, right? You'd still recognize it as a bird. Not because we've seen this particular kind of bird, no, but it matches our model. It matches the pattern in our mind of what makes a bird. And once you have these patterns, same thing with machine learning systems, they can not only recognize birds, but just as we humans can draw birds, so could a machine then, right? Based on these patterns, we can recognize new instances of whatever it is we've learned, be it birds or draw instances of this. And here's the thing you should really realize. Many people think that after the machine has learned this pattern, has found this pattern of recognizing whatever it is. Let's stick with the example of birds, right? Then if you then open the hood of the machine, and you look inside, you can see these patterns, right? That's not the case. That's what people think. And you should compare it more with what you see when you open the hood of one of these machines is a lot of numbers, and you have no idea how these numbers relate, right? It's kind of like if you guys would open up my skull, lift the top, look inside, you would not see my memories. You would not see my thoughts, right? You'd see gray matter, which is pretty much what you see when opening a machine. And that's a fundamental idea. So once the machine has learned these patterns, if we open the machine, we don't see those patterns. We need to do a really big effort to understand these patterns. And if the machine is really big, like a modern AI system, like GPT models, those amounts of numbers are so huge that we cannot really even begin to understand the patterns, right? But this has a consequence. And let me explain this to you by story. In 2019, there was a group of researchers who trained a machine learning model to recognize species of fish in images. So they showed it photos of fish, and the machine had to say, this is a herring, this is a cod, this is a salmon. Those are all fish we eat. I'm not a fisherman, so I get my knowledge off the plate, not from the water. But this is a relatively simple task. They did that because if you take a simple task, it is possible to open a machine and start poking around in these numbers and seeing what patterns the machine found. Now, after the machine successfully learned to classify images of fish, and they started looking inside the machine of how these patterns were, they found something weird. They found that the pattern of a fish called a tench, which is kind of like a pike, I think it's called a zeelt in Dutch, for those who speak Dutch, like the Belgians and the Dutch in the audience, but in English there is a tench. It's a big sweetwater fish. They found that the machine would recognize a tench because of its fingers. Now that's weird, right? Do you agree? Why would they recognize a fish by its fingers? So they started looking into this. And what they found is this. Realize the tench, I told you, the tench is a big fish. So if you catch a big fish, what do? You make a picture, right? You post a picture online, which is the data that they use. Now, here's the second takeaway, and this is very important, right? So, was the machine wrong? No, exactly. Someone said no, very good. Because the machine is right. The machine is programmed to find patterns. This is a pattern, right? It's perhaps not a pattern we expected it to find. It's also perhaps not a pattern we wanted to find, right? Because it's no use if we use now this machine to classify tensions that are not held by human fingers, right? But the machine works properly. So not knowing how these models internally are constructed from machine learning is very relevant. It's very relevant. This happened to Amazon, the big parcel shipping company, as well. They decided, I think it was 2015, to train a machine learning model on resumes that they'd received. So people would apply at Amazon, send a resume. Sorry. And then they were either hired or not. And they had 10 years of this data, of resumes plus the decision that they made. So they trained a machine learning model. Can you come up with a pattern why we hire people? And the machine did. It was brilliant. It worked really well. It could really well predict if Amazon would hire someone. There was one huge problem. Whenever the resume had the word female, women, woman, anything, female related, reject. That's a pattern it found, and that had to do with the fact that Amazon was mainly, in the beginning, in the early days, a very technologically based company, and therefore it attracted more men, and therefore more men were relatively hired. Now these are all patterns that you don't want the machine to use, but you cannot really avoid it, so they just shut down the machine. In fact, they also trained it also on the cover letters, so not only the resumes, but also the cover letters. And they found even that certain phrasings, not even containing the word female or related words, but certain phrasings that we know are statistically more used by females than by men, were enough for the machine to say, don't hire. Now that's not good. This is known as the bias problem, right? This is the base of the bias problem. You've probably heard of it before, right? Now, now I talk of these machines, so I went from AI to machine learning, right? But it's still a magical concept. How does the machine learn? So let me tell you a little bit about that. I'm going to do this by way of a story that I constructed myself to explain this to you. Now imagine, it's a thought experiment. Imagine I give a machine a list of words. These words are semi-randomly constructed. I was sitting behind my desk at home coming up with words, and then my son came in and started talking about his favorite football player, Kylian Mbappé. So that's how he ended up in the list. Anyway, they're just words, terms. And what can a machine do? This is a thought experiment. What can a machine do with this? Not much. It can order it alphabetically, but I've already done that here, right? But it could, for example, order these words by length. Yeah, not very useful, but it could. But that's about the scope of what the machine can do, because it has no idea what the difference is between a Rubik Cube and Kylian Mbappé. It really doesn't. How would it know? But that changes when we give it data. Now, imagine that you're a programmer, and you write this really simple piece of code. It scans the web for texts, books, newspapers, whatever. And it looks for these 15 words. And then whenever it finds 2 of these words in the same text, it makes a note. I found these 2 words in the same text. And it also looks at how close they are in the text. How many words are in between? Are they far away or are they close? And it just does nothing else than just log this. That's a simple enough program. You can imagine that writing that, right? Now, that has a consequence, because if you do that, then the machine, really what it does, it calculates the distance between words occurring, these 15 words, occurring in human-made texts. And that distance can be visualized in a plane, in a space. In this case, a 2-dimensional space to make it easy on your eyes. It should have been like 100-dimensional, but we humans suck at that, at understanding that. For machines, the difference between 2 dimensions, 3, 4, 10, 100 is irrelevant. So basically, by writing this really simple program, you can construct a mapping of words into space. We call that the latent space, and this idea is based on the distributional hypothesis. And the distributional hypothesis from 1954 by Professor Harris, it says that words are likely to co-appear in a text if their meanings are related. Now this is what we see here. Look at this mapping. The word cat and dog and cat and tiger are very nearby. Or the words Leiden and Utrecht. And for those who don't know, Leiden is a Dutch city where I work. Utrecht is a Dutch city where I live, right? So in this space, it's here 2-dimensional, but you should imagine it's high-dimensional. The location of words if words are near together, their meanings are quite likely related. We call this space the latent space. Now, imagine the following. Imagine I write down the coordinates of these words, right? So in this case, I use a letter-based coordinate system, but letters, numbers, it's all numbers to machines, right? So, and then I make a new list. There we go. I make a new list. So I now have a new list of the original human words, angry, animal, cat, car, etc., and their coordinates in this example, in an imaginary 12-dimensional space, right? It can be any number of dimensions, but these are just the coordinates where these words reside in space. Now this may look like abracadabra, but look closely, look here. When words, basically they're the coordinates, so when words are nearby in the space, like the two ones I marked red, their meanings are quite likely related. So the meaning of the word tiger, or the meaning of the computer word for tiger, let's call the column B computer word and column A human word, right, are quite likely related somehow. And so are Leiden and Utrecht. Now I'm going to take this thought experiment a step further, right? What I did is I went to randomwordgenerator.org, which is a website, and I asked it, create a random word for me. And it came up with, okay, there we go, ulirata. Do you have any idea what ulirata means? No, neither do I. I have no idea. It was created by a random word generator. It's a non-existing word. Ulirata, what is it? Is it cat food? You know, is it river? I have no idea. Right? If we make up a random word as humans, using a pair of dice, we don't know what it means. But wait a minute. Watch this. Now I'm going to make up a random word in the computer column. This one. The VDLA, ECRF, WDLF. There it is. It's a random word. It's random. But wait a minute. Look closely. It resembles the computer words for cat and tiger. So this is very likely, it's a random word. I made it completely randomly, using a pair of dice. But very likely, to the computer, it has a meaning such as lion, maybe, you know, or panther, or leopard. No? Okay, can you follow me so far? Yeah? Okay. You may be thinking, okay, Maarten, where's this going to? But what I just showed you is that for the computer, just the value of data, adding data to these words is humongous. It creates a form of meaning for the computer. So it created its own words that if the meaning is similar, the words are similar in form. I wish we had that as humans. I would love that. We don't. We make up stupid languages, very stupid languages. Computer doesn't. No. So you'd be thinking, okay, so yeah, we can create random numbers, and they have meaning to the computer. Yes, but I'm also telling you that everything inside a computer is a number, be it words or be it photos. Now look at this. These are people that don't really exist. They're made by the website thispersondoesnotexist.com. They're very realistic. How are they made? Exactly as I just showed you. Exactly in that way. That's it. They just, instead of feeding the machine words data, they fed it human photos data. And the machine started seeing connections between photos, connections, recognizing patterns. And then they gave the machine a random number, and boop, out came the lady on the left. They gave it another random number, boop, out came the gentleman on the right. Now this is really how these machines work. The fact that the quality is so high, that's a different story. I usually explain that as well, but I'm not able to do that in 20 minutes. So I'm now going to wrap up very quickly. I hope you've learned something already, right? Now the question I want to end with, is the machine creative? Because it's a more interesting question you would think, right? And asking whether a machine is creative is a very difficult question. People have been doing that for a long time, mainly artists. If you are a researcher, talk to artists. This is one of my favorite works by Jean Tinguely. It's a cyclo-graveur. It's a bicycle contraption, and when you start pedaling it, it makes a drawing. Now, my interpretation of this work, and I'm not the only one with this interpretation, is that what Jean Tinguely does is he asks the question, who's creative here? Is it this weird-ass machine? Is it the person pedaling? No, because there's even a book to take them mentally away from the process. Or is it the inventor, Jean Tinguely himself, who's creatively responsible for the drawing? So this is the way that artists ask these kind of questions about machines and creativity. And it didn't stop in 1959 with Jean Tinguely. This is a performance that I've also been to one of the instantiation of with Dragan Illich. It's the same question. Who's creative here? Is it the giant robots? Is it the creator of the system who is Dragan Ilic, or is it basically the pen that is Dragan Ilic as well, right? So it's just reason. Let me stop Dragan here, sorry. So it's a difficult question. Now, one other way to answer it is to go back into history. To answer difficult questions, always first start with the artists, right? They usually just ask the question, but they give you new insights. Then go into history. Who've been thinking about it? And when we look there, we end up with this lady, Ada Lovelace. You may know her name. She's been in the news quite often, although she's not alive anymore. She was communicating in the, let's say, first half of the 1800s, sorry, with Charles Babbage, who was making the analytical engine, the first programmable machine that he never actually completed. But she was already writing code for a machine that didn't even exist yet, and she was unbelievably smart. And she said something really relevant. She said, you know, this machine you're building that Charles Babbage only envisioned as a number manipulator, as a computing device, she said, you know, maybe in the future it can compose music. And this is a giant leap in history, I think, this idea of her. It's transposing the idea of mere number manipulation to something that has meaning for us. But she said, it can only do that if we tell it exactly how, right? That's not true. That's not true. We don't need to know how to recognize a bird for a machine to do it nowadays. And the reason is, again, learning. As Alan Turing said, you know, once machines start to learn, they will be creative, right? But this still doesn't answer our question, is it creative? I told you, I'm a nerd. I need to categorize stuff. Put it in little boxes. You know, that makes me happy. So what nerds like me do is we look at theories from cognitive psychology, such as those by Margaret Bowden, who is a creativity expert on human creativity and machine creativity. And she says, well, there are 3 ways for human to be creative. And I'm going to discuss 2 of those shortly. I'm going to skip the first one. But because the last 2 are relevant to computing systems as we have them now. And the first one, let me explain it to you by way of these paintings. And I'm not sure if you know by who they are, but Amanda gave it away already a little bit by mentioning the happy accident. Any idea? Bob Ross, very good, very good. This is just this gentleman. He was a TV painter guy. And why do you know it's Bob Ross? Why did you know that these paintings were Bob Ross? Because you recognize them as Bob Ross's. Why? Because they have this unbelievably stylistic recognition in them. It's very easy to recognize them in the style of Bob Ross, because everything Bob Ross made is within this stuff, from this style, from this paradigm, from this conceptual space, as Margaret Bowden calls it. In his mind is this idea of how to create a painting. Big things in the background, moving tiny details in the mid-front, coulisse stuff on the side. And he made everything according to this pattern. There we are again, pattern. According to this style, according to this conceptual space, as psychologists call it. Now, this phenomena, Margaret Bowden calls exploratory creativity. It's when you find new ideas within an existing conceptual space. So that's what Bob Ross does, right? And when we look at this example that we saw already, that is exploratory creativity. We've fed the machine many faces. It learns the pattern of the face, the human face. And every time we ask it to generate something randomly, it comes up with a human face. It will never come up with a cup of coffee or a horse. You know, it comes up with a face because that's the pattern in it. So that's exploratory creativity. But there's another form. Now imagine yourself visualize a Mondrian painting. Do you know Piet Mondrian, the painter? Imagine one of his paintings. You're probably not imagining this, but this is by Piet Mondrian in his early career. Right? You're probably imagining something like this. This is his late career. Now, what we see here, Piet Mondrian, Piet Mondrian. Piet Mondrian early days, Piet Mondrian late days. That's a huge transformation. That's a big transformation. Now, that is called transformational creativity, right? So you step outside of existing patterns and you create something completely new that does have value to humans. Picasso. Transformation. These are 2 female portraits by Picasso. Picasso was 45 years in between them. Look at the transformation. The Beatles are known as being really transformative, creatively transformative, creating a new style of music. Now, the question is, do we see this in machines? No, we don't. We don't see artificial intelligence machines doing this. The question is, can they? That's the question computer scientists always ask. Can they? Can a machine do that? Many people say no, because for that you need inspiration. You need to grow up in Liverpool in a socially difficult time maybe, like Paul McCartney and John Lennon. Or you need to love jazz music and visit the city of New York, like Piet Mondriaan. Now, these are all these things that even ChatGPT says humans don't have, machines don't have it, so they can't. I don't agree there. Machines will, and I have reason, but I will not go into reason now because I don't have time. But I don't see a problem there. Machines can understand what we like, that's not a problem. Can have inspiration, it's not a problem. So what is a problem? Not much. But realize that this is the way. We do not have that form of creativity in a machine yet. We do have exploratory creativity. And I hope you learned something. I'm going to skip the last quote. And thank you very much.